This constancy of c once again stems straight from Maxwell's equations. These equations, as we've seen, tell you that the speed of light is 1 over square root of epsilon 0 mu sub 0. But there is no particular system of reference that you are required to use to solve Maxwell's equations. Before Einstein, most people thought that c was the speed of light with respect to a particular medium, which was called the ether. But this idea is in violation of the Newtonian idea that all inertial systems of reference should be equivalent. If you remember, we used the fact that Newton's second law, F equals ma, can be used regardless of what the speed of the observer is. This equation is valid for all systems of reference that have constant velocity. Now, not only the idea of ether violates the equivalence principle, but its biggest problem was that ether could not be found. Scientists believed that it should be there, otherwise they couldn't make sense of the electromagnetic equations and the speed of light. But the problem was it couldn't be found. Many different kinds of experiments were done towards the end of the 19th century, and each one of those experiments failed to find any evidence that the ether existed. Evidence of this would have been, for example, to find if they should have been able to measure a difference in the speed of light as it moved in the speed of two light beams moving in opposite directions. If the ether existed, one should be able to measure that the speed of light in one direction is different from the speed of light in the opposite direction. To understand this, one can think of the following situation. Suppose that you have a bus, and somebody inside the bus decides to throw a ball. That ball can be thrown in this direction, or it can be thrown in this direction. The bus has a velocity with respect to the ground, and the question is, how does this observer measure the velocity of the ball? How much is the velocity of the ball with respect to the stationary observer on the side of the road? Well, that velocity is going to depend on whether you throw the ball one way or the other. If you throw the ball forward, the velocity of the ball with respect to the stationary observer is going to be the velocity of the ball with respect to the bus, so this vector, plus the velocity of the bus. So the resulting velocity is that vector. But if you decide to throw the ball in the opposite direction, then to the velocity of the bus, you need to add, or better subtract, the velocity of the ball, and that gives you a resulting velocity that is smaller than the velocity of the ball if you had thrown it forward. So in this analogy, the ball is playing the role of light. The bus is the medium, the special medium that supposedly should be used to measure the speed of light, that supports light, and the observer here, well, is an observer that is not moving with the ether. So if the observer is not moving with the ether, sending light in this direction or sending light in that direction should have consequences in terms of the velocity of light as measured by this observer. One of those velocities should be bigger than the other one. And the only system of reference in which the velocity of light should be 3 times 10 to the 8 is the system of reference of the ether. If you make a measurement of the speed of light and you find, according to these ideas, and you found that it was 3 times 10 to the 8, that means you are moving with the ether. But if the speed of light that you measure was different, then that means that you're not moving with the ether. So experiments trying to find this difference in the velocity of light in opposite directions were done. These and many different kinds of experiments. And the result of all these experiments was that the velocity of light in every case was always measured as being 3 times 10 to the 8. This was the situation at the end of the 20th century, and it was driving scientists crazy that they could not explain why the ether could not be found. So Einstein comes in and provides a different approach to the problem. So he says, the experiments are telling us that the speed of light is the same, is a constant regardless of the speed of the observer. So let's believe the experiments and postulate that the speed of light is constant. It's a law of nature that the speed of light does not depend on, for all observers, no matter how fast they're moving, the speed of light is always the same value, 3 times 10 to the 8 meters per second. So that was his first idea, is take the result of the experiments at face value. Second idea was that we should not discard the idea of inertial frames of reference as being equivalent. He went further and said that it should be required that all physical laws must be the same for all observers. Notice that if the velocity of an electromagnetic wave, which is equal to 1 over the square root of epsilon 0 mu sub 0, if it was only true in a particular system of reference, then Maxwell's equations would also be valid only in that specific frame of reference. Now maybe Faraday's law would only work for some observers but not for others. Maybe depending on the speed of the magnet you would find induction in some cases, but not in others. Now at the time when Einstein was working on these equations, Maxwell's equations were pretty well established and had been tested, and nobody had found any deviations from Maxwell's equations that led you to believe that they were valid only in a particular system of reference. So using all this information at hand, Einstein postulates that all physical laws, including Maxwell's equations, must be the same for all observers. That includes, of course, the speed of light. So all physical laws, is the second postulate, must be valid in all inertial systems of reference. From postulates 1 and 2, using those, Einstein was able to show that there is time dilation. There has to be time dilation if the speed of light remains constant. Once you have shown that if the speed of light is constant, then there is time dilation, it is a short step to conclude from time dilation that there's also another strange phenomenon called length contraction, which tells you that the length of objects is different for different observers if they're moving with different velocities with respect to each other. So once you have shown that the length is relative, that the length of an object is relative, then the next step is to derive what is the equation that allows you to connect the velocity of an object with respect to two different systems of reference. What I'm talking about is a modification of the Galilean transformation of velocities that takes into account the relativistic effects of time dilation and length contraction. Einstein showed that what equation you should use to transfer the velocity from one system of reference to another, and using that result, and so let me write it here. So length contraction, from this he arrived at the transformation of velocities, and from this, using that equation for transformation of velocity and conservation of momentum for a situation of two objects colliding, having a collision, an elastic collision, conservation of energy and conservation of momentum, from those equations you can arrive at the conclusion that the mass of an object depends on its velocity. It is the only way to satisfy the equations from relativity and take into account the time dilation, length contraction, and transformation of velocity equations. Once you have concluded that the mass of an object depends on the velocity, you are forced to conclude that the energy of an object actually can be written in terms of the mass of the object. That when you add energy to an object, that energy actually goes into its mass. Therefore, mass is energy, and energy is mass. These were two very different, separate concepts before Einstein. After Einstein, mass and energy turn out to be the same. There is a very important proportionality constant, which is c squared, which is an enormous number, 3 times 10 to the 8 squared. The fact that that number is so big, actually, and that there is a connection between the mass and the energy of an object, is what actually allowed people to understand and to solve the mysterious problem of radioactivity, which was a problem. Radioactivity had been discovered a few years, maybe 10 years before Einstein's relativity paper, and it was a mystery because it was observed that a radioactive material emitted an enormous amount of energy. There was energy coming out of the object, and nobody could figure out where that energy was coming from. The conservation of energy said that energy is not created or destroyed. Therefore, that energy that is coming out of a radioactive substance must be coming from somewhere else. Must be the result of some other form of energy being converted into this energy that gets radiated out of the object. So relativity says that what is happening is that a small amount of the mass of the uranium nucleus is being transformed by nuclear reactions into just pure energy that gets radiated out of the system. Once you figure out that mass can convert it into energy, and that a tiny amount of mass can actually give you a great amount of energy, then you get people thinking about the possibility of destroying a small piece of matter and releasing the enormous amount of energy associated with that. If this could be done, then it would be the ultimate weapon. And with this realization, the race was on between Nazi Germany and the US to be the first one to produce such weapon, which the race that culminated with the nuclear bombing of Hiroshima and Nagasaki 40 years after Einstein's publication of E equals mc squared in 1905.